Okay, so this has been promised for a while. A full STAR-CCM tutorial. So let's get into it. Let me get rid of it. First, we close this. Yes, this is our STAR-CCM. How you open it, your properties, output over here. Let's go pretty much there. You can press this button, or you can go File, New. Pretty much it's very important. You can choose a template. I suggest you don't. Pretty standard stuff. This is for optimization. This is, of course, for our simulation. Pretty much parallel and local host. So this is going to involve parallel processes. Pretty much, it'll be at 2 when you open it up. But you want the max physical cores as that number. So let's go into Task Manager. And go into here, 8 cores. So I'm going to make this number 8. I press OK. That's going to make a completely new file. And here it is. This is our STAR-CCM file. Nothing here, completely empty, completely blank. And we're going to, from scratch, make this into a simulation for a front wing. So there are 2 ways to import. For your next step, import surface mesh, which is going to import geometry pretty much, or import into 3D CAD. Now, importing into 3D CAD will bring you directly into the 3D CAD program. This will give you higher editing ability. Now, if you just import into surface mesh, you can, of course, also edit in the STAR-CCM CAD. So I just do this purely for convenience. So let's go to front wing. Of course, this is, let me do that again. Import surface mesh. I have it open. This is where the file is. You have to navigate to this directory, but I'm already there. Press OK. Now it's going to import the part, and it's going to open up a geometry scene. So let's go to scenes here. Our one geometry scene here was not there before. It's here now. Now, let's say we delete the scene. Oh no, there is unfortunately not a Command Z. Control Z. You cannot undo that. However, what you can do is go here, geometry, and we'll make a new scene. You can also go here, new scene, and choose one. Of course, right now you see if I look at this, it's not a completely straight geometry. It's not flat. It's because we're in perspective viewing mode. We want to be in parallel. Well, I prefer parallel. So if I go front, side, top, and you'll notice that when of course, I'm pressing S, F, and T. So I press S, side, F, front, T, top. Press F, I see the side. Now this is because STAR-CCM assumes that, well, you're going to face, your geometry is going to face the negative x direction, and that flow will face the positive x direction. We want to make that the case. So let's go here. There are 2 ways to rotate geometry. The first is just to go right click, transform, rotate. Now this is very useful, of course. However, once it's done, it cannot be undone. There is no history of it, and of course Command Z doesn't work here. So let's just do this. I know by heart that this is 90 degrees. I'm going to press apply, and it's going to rotate for me. Boom. However, I can press Control Z, and maybe I want to rotate 30 degrees instead of 90 degrees. I can't be doing that. So let's undo that. 1.5708. Now we're back where we started. What we can do instead is go to Operations, New, Search Preparation. The 2 important ones here are Offset and Transform. Offset, very useful for meshing. So let's click the front wing, here, Transformations, here, Rotate. You rotate here. Let's set that as our axis of rotation, and we want to be in degrees and 90. So this is much easier, more accurate. You don't have to memorize the 90 degrees in radians. You go execute, That is, of course, wrong. Negative. And of course, if you do it wrong, you can easily change it, re-execute, and it will re-execute for you. One of the advantages of having it in operations instead of just doing it out here, we're doing Boolean out here. Speaking of Boolean and stuff like that, there is a pathway. See, we want to do external flow on this geometry that we have right here. How are we going to get there? How are we going to get the domain that represents external flow? And it's fairly simple. What we're going to do is recognize that each of these are separate parts. Every single one, we're going to unite them all together. And then we're going to make a big box, and we're going to subtract that unite from the big box. And that will get us our wanted, desired geometry, so to speak. Now, new Boolean unite. I'm going to choose this, choose all of them, make sure it's in CAD. Sometimes it's not necessary to be in CAD, but it's usually good to be in CAD. Unite in CAD, I want to press execute. What this is going to do, it's going to create a part called unite that is the result of all these parts united. It's not going to delete this part is still here. But I don't want to see this, and I want to see this show. These are our displayers. And it's a good time to actually go into displayers in this little scene plot tab. Whenever you have a scene open, whether it be CAD, whether it be this, whether it be something else, you're going to have surface from surface and outline. And we're going to have parts, as you can see. Becomes especially useful when doing post-processing, having all your parts or cycling through your parts. Because you go on clearly, you see that these are all hidden and these are shown. If somehow these disappear and, right click, show doesn't do anything, you can add them right here. You go here and you can add more parts. Let's close this. So we have right now, we want to check, which is very important, is this. Curves intersection. Very important that we check this. Very important we have perfect intersections. Now, of course, if you see imperfect intersections, you will notice them right away. But we have perfect intersections right now. And what happened is if this was imperfect, there would be like, maybe this part would show up, but this wouldn't be here. It would be all weird and it wouldn't look like an airfoil or like the profile we've chosen. So, and if that ever happens, which it will, inevitably, it's not even a CAD thing, it just will happen sometimes. You're gonna want to come here. Maybe it's this element right here. We're gonna go right click, edit in 3D CAD. And of course, this is our 3D CAD plot. We have our simulation scene plot, which is 3D CAD view now, and 3D CAD. What we can do is, which just allows us to edit the geometry. If we want this intersection to be made apparent, what we would do is we right click here, and solid, and we'd, well, it's a small amount. Okay, update, close. Then we come here and update. Then now, if that intersection didn't work before, it would work now after we re-execute both the unite and the transform. The reason that perfect intersections are very important, the most important, is because if you don't have perfect intersections, your mesh will simply not work at all. It will fail, and you will be sad and have done work for nothing. So that's just what it is. You'll have to come back here and, make sure that's correct. Now we want to build our box. So we're going to unite everything and make a big box, and we're going to subtract the unite from the big box. Now, there are some general principles, or actually, let's go on this. How would we make this big box? First, we can go new in 3D CAD model, and just XY, right click, sketch, box, and just go boom, box. We have a box now. Life is good. However, I do not suggest this. It's just a lot of work for nothing. Instead, there's a pretty simple way to make a box or simple geometry. Right click parts, new shape part, and you can make all of these simple geometries fairly easily. Very useful stuff. So let's go into block because all it is a block. And I'm going to talk now about CAD prints, or sorry, CFD basic principles. Now, usually you can be making it bigger. The domain should be bigger than what I'm telling you, but the minimum size it can be is whatever this length is, 4 of those lengths in front, 8 of those lengths behind, and 4 on top. And of course, for this simulation itself, the ground is very important. The ground affects the front width. So we're not gonna, mess with the ground. We want to be at 0. But, well, 0. But if we were to have, say, a wing, and we want to simulate this wing acting in, the sky, we would do this, of course. Now, of course, this is all math, 4 heights above, 4 heights below, 4 lengths in front, 4 behind, and of course you want to remember width, 4 widths to the side. This is all math. However, I have all these numbers in a handy dandy template that I have made for the front wing specifically. I also have one for the full car right there. But let's open up the front wing template. And pretty much what this is everything that I'm going to show you has been done to this already. All the post-processing tools are here. All the geometry is here, except of course the front wing itself, which you would import and then you'd add to regions and then add to the mesh, which pretty much allows you to set up a sim in like maybe 15 minutes. But enough of that. Parts. We have domain here. Now, of course, copy, paste. The copy paste function is of course very finicky. It just is. So it doesn't matter. I can go here, new shape part, block, create, and just take the 2 points, -5, 0, 0, and then okay, that's 9, -5, 4. That is our domain for our front wing. All we have to do now is go operations, new, Boolean, subtract. We select both the block and the night. Although we are skipping a step. Actually, let's go back and do that step. Let's rename this domain. And of course, right now, we need to be able to separate later on our inlet, outlet, and symmetry planes all around, and the floor. So let's do that right now. Right click, split by patch. Here, this is the top. This is symmetry 2. This is the inlet. This is the symmetry 1. This is the floor. And finally, this is the outlet. Notice we can't create this, so let's go close. And this is the default block surface, so let's name it outlet. Very important we separate all these because, of course, air will be coming in this way, going out that way. This will be a moving floor. And of course, these will all be symmetry planes. So now that we have all of this, we can go make our subtract. I will subtract the domain. Let's not do that. And unite. And our target part will be the domain. So execute CAD Boolean, and then we're going to execute. Then at this time, we're going to hide everything. Hide. And we're going to show only the subtract with both displayers. And then let's check. Always check to make sure your geometry is there. And voila, it is. There it is. And everything is going well, everything's going good. Now what we have to do is we have to go down to continue. Now what continuous sets is your pretty much your physics. So let's go right click, new, physics continua, models, double click that. Now we're going to use the models used mainly in Rensselaer Motorsport, 3-dimensional gas coupled constant density, because we're slower than Mach 0.3. Steady, implicit unsteady is for those who want to try transient sims, which means that time passes. Steady state is fine with us. We're good with steady state. Steady state gives us very accurate results, less time. And of course, what did I just choose? Laminar. No, we don't choose laminar, we choose turbulent. In the K omega turbulence model. Of course, this is all loaded in the template. You'll see. Let's close that. Now we have our continua. Now, seeing as our regions, we need to make sure we separated here. We separated, and even subtracted, it's separated the floor, the inlet, outlet, all this stuff. We need to now make them inlets, pretty much, make them outlets or floors. We'll make a region. Of course, we're going to call this region subtract. Of course, boundaries. For every one of these, we need a boundary. Every one of these, not that. These surfaces, we need a boundary. So we're going to go make those boundaries. So, I don't know how many boundaries it is. I'm just going to make a bunch of boundaries. So if this is domain boundaries, we need 5 of those, and then wheel, and then wings. So let's start naming these, of course. This is the pain. Kind of, it's kind of a pain, which is why I like using the template. Of course, I spelled inlet wrong. Maybe I spelled it right. I don't know what I'm doing. And notice I put sim2 and top together. They're both going to be symmetry planes, so don't have to deal with it. Put them both in the same thing. Wing and wheel. The reason wheel is separate is because the wheel itself will rotate. Of course, now the reason the floor is separate because the floor will move as it would. And now let's go and give each boundary different conditions. Right now they're all the same wall. We need to change that. First, our floor needs to move. So let's go to tangential velocity specification. Right now it's fixed. We don't want that, we want it to move. So we need to go here and go vector. Now physics values, you can give a relative velocity, and we're going to give it 17.8116. What this is going to do is create a boundary layer and give it this velocity. And the floor is going to be given that velocity too. Now inlet, we don't want it to be a wall. We want it to be a velocity inlet. We want to change this boundary nor to components, because you always want components. You want to make sure it's going in the right direction. And then for 17.8116, which is 40 miles per hour. Most of our sims will be tested at 30 or 40 miles per hour. It's a simple conversion. You can just put it into Google. Outlet is pressure outlet. Don't mess with anything else. Symmetry 1, symmetry plane, of course. It's simulating only half the wing with symmetry in the center. Once again, these two are also symmetry planes. Wing, well, is just a wall. So it's fine. And wheel, but wheel is very important. Wheel is given a local rotation rate. Selecting this rotation rate will rotate around the origin or the reference frame, but local rotation rate will let you select an axis, which I know from CAD in inches. That is our axis. You know that by heart. And of course, the axis, the direction of the axis is 0, 1, 0. And of course, I don't know this, so I'm going to go here, and I'm going to go into the regions of this one. There, oh, there we go. Wheel, and the axis. And this is our angular velocity. This is also some calculation, but, why do it when you already have done it? Now we have all our regions set up. we just need to load in the parts. So we choose subtract, and actually most of these will load in for us, and they'll actually change color. Look at that. Temperature planes are blue, so if you don't see the colors, so you're doing something wrong. And gray is walls. So here, as you can see, floor, it recognizes the same name, same with inlet, same with outlet, sim1. It doesn't do top, sorry, sim2, but we can change that. Nothing's in wing, we want to change that. We don't want the entire front wing to be rotating, so let's select all of that. And, well, the wheel is good. So now we have all our regions. And the last thing really to do is set up mesh, and then we can run. Of course, there's also post-processing. It's honestly just copying, because it's just a lot of repetitive datum plane, section planes. But right now we want to do mesh. Now, the thing about mesh is we want it to be consistent. If we change the mesh, make it finer or less fine, with the same geometry, you'll get different, values for your reports. What you also need to do, reports. And this is very important that you keep the mesh consistent. So which is why I'm just going to copy over the mesh. Boom, copy. We go into here, Control V. And there it is. It even knows it's subtract. However, we're going to miss all these custom controls. We need to load these in. We need to make these. Now, of course, these default controls are numbers given by Chris Penny, and pretty much everything is based on this base size. Or everything here definitely based on this base size. So if you want to make it finer or more granular, you can change this number and it will affect the entire mesh. Now let's get into custom controls. First is the surface control, chord less than 2. This obviously refers to wings of less than 0.2, and that is 0.2 meters. I know by heart that that is the second and third elements. So I'm going to go here, boom, boom, boom. Sorry, and select the second and the third elements. And they're going to light up. Now you know it's selected. Now I know greater than 0.2. Now, of course, if you're doing a full car sim, you actually have greater than 0.2, less than 0.4, and you'll keep going. But the front wing has pretty small chord length, so I only have these two in for the front wing template. I know that the main and the first element are greater than 0.2. The curve control, just select the entirety of this. That should show up. Detailed lane 800. Now, what is our detailed lane? We simply don't have one at the time. Actually, let's get that for now. We can do these three at the same time. Let's go to end plate. We know what end plates are. Let's go choose the outer end plate, the inner end plate, and the strake. And those are pretty much the end plate looking things. Now, these three, of course, these are surface controls. This is a curve control. And these are volume controls, which control the volume. Now, these just make it, this domain makes it actually very huge. Makes it pretty big. You can look at these values, try to edit these values, but most of these values are good. But pretty much this edits the surface of things and the volume around the surface. This edits the curve and the volume around the curve, and this is going to edit the volume of whatever you give it. So let's make this detailed lane a lane where we want detail. And this is actually pretty easy. So we're going to go to parts, new shape part, block. Let's go. And we can just make the lane pretty easily. Boom. Boom. Make sure we're filling all that gap. Well, this is the lane where pretty much wherever the geometry is. We want to keep this lane consistent, because if you don't and you just make it like this, you're gonna have error doing wacky stuff. This we go from huge mesh out here to very small mesh. We want to keep this lane consistent. So let's create that, and we're going to rename it detailed lane. And we're going to go to the automate mesh and custom controls 800. 800 refers to how much bigger the surface mesh is, obviously. Well, not really obviously, but it's just how I've labeled things. Detail lane, okay. And that's our detail lane. Offset, 0.3, 100. Now this is where we use that offset we mentioned earlier. So we're gonna go, we actually want to use this. So actually we're gonna go here. Operations, new, here, offset. Let's make a, and I'll choose unite. And I'm gonna make 2 of them. You can just, actually yeah, this is very bad. Because you actually want the mesh under. Someone delete this real quick. You want the offset over the mesh. Then you'll be able to use the offset because this is, I don't know why, it's just how it is. It takes in things from top to bottom. If the offsets are below the mesh, you can't use the offsets for the mesh. It's how it is. So let's offset. Now it's unite, and of course we wanted, this says offset 0.3, so 0.3, offset 0.3, and then of course let's rename this offset 0.3. Whereas this is offset 0.15, so 0.15, and you'll see what this does. It's actually pretty insane. It really helps improve the mesh. Of course, you have your offset up here, so let's rename these two. Offset 0.3. So we're gonna go execute, and we're gonna go execute the other one, and then we're gonna load them into the mesh. So right here, or if we get to choose from all of our parts, offset 0.3, which pretty much makes this more detailed than the rest, and then offset 0.5, which makes it more detailed in the smaller offset of the entire geometry. And what this does is pretty much makes the mesh insanely efficient while being accurate. Now tire 25. This is mainly a block that's going around the tire. This is also very easy to make. Simply use the block command. If we want to know about tire wake, and this is how we do it. We want to solve the tire wake. Since the tire will be spinning, we want our area behind the tire to not to converge, pretty much to converge. Let's make this block rough estimate. We want to get all that tire wake. Just get all the tire wake, and that's how much you want. About that, actually, we can make it a little bigger. Create close, and we're going to call this tire. And we're going to put that in here, tire. And now, pretty much, almost everything is done. We can press execute, we can run is here. Press run right now, it will say, okay, press volume run right now, it will say no volume mesh. You need to mesh first. But everything is set up. You can go mesh or run. The problem is we can't visualize the solution. Now, how it runs through most to visualize the solution, understand what's happening. And well, this hasn't been done. This is mainly me, what I've done, but it's section planes. So if I open up this section plane, so I'm going to copy these straight over from. These are pretty easy to make. If you want to go here, you go. Section planes, yeah. So let's close all of this. Go right parts, right click, new part, section, plane, and then you get to move it with this. No displayer is always good. And you'd pretty much, yeah, set where that plane is. Then you can make a scene. No, I'll just show you. So I've made a ton of these already, and it's a ton of manual work, so I'm just gonna go, well, I can't copy, but let's copy all of these over. Copy, paste. Wait for it, it's gonna load. Yeah. But yeah, there go, all the section planes are loading in. And this is gonna give us a representation of pretty much the flow. Parts to subtract, of course, and these are all our planes. And you're gonna see what happens when I show you, and how to do post-processing when I show you. but these planes are very important for visualizing the flow. Also, here you can add in y planes, which face the y direction. I'm going to show you this, and z planes. Go back here, which will show you the top view. Also very useful to look at outwash, stuff like that. How air is going around the tire. Just all these planes are useful. The reason why I have all of them, and they're just really useful. Now, finally, what we need to do is how we're going to visualize these planes. We need to go to scenes. New scene. Let's go to vector. So we want to visualize velocity in each of these planes, and we're going to go. I always like to do this, and then get rid of this, and then we just load parts. We'd load in our planes, all of them, and they don't show up because you don't have a mesh or, well, anything really. But we also want to go to vector, glyph. Glyph is bad. We want this. And pretty much that's how you're going to visualize the solution. And finally, the most important thing is reports. Now, you can run a CO report that involves work and doing a lot of stuff, but I just run downforce, drag, and downforce of just the wing. And this is pretty simple stuff. Pretty much, you're going to go new. There we go. Let's actually close these scenes. New report, fluidometric energy, force. Of course, force coefficient is here. If you want a frontal area, you can calculate the frontal area and then do a force coefficient. I find that it's less useful overall. Let's go to pounds. Reference pressure, 0, make sure it's 0. Direction, downforce, so 0, 0, -1. And then you just add in the parts. So regions, wheel, wing, boom. And then after it's run, it will show you, let's rename this to downforce, 5/2, because it's half the wing, of course. And when this will run, you actually visualize how it changes by creating, monitor, and plot from reports. So it'll make a plot. It'll plot your residuals, which of course, as residuals go down, you converge, and your downforce, which if the downforce level is off, then it's pretty accurate. Now, the golden thing is you can have the residuals not totally converge to 10 to the -3, but if your downforce plot and your drag plot level off, it's pretty accurate. Your sim is pretty accurate, and you've done a good job. Now, of course, if you see downforce fluctuate up and down, maybe you need to be finer, maybe you need to be more granular. It depends. Now, this is pretty much everything that you need to set up everything. So let's just go to the finished solution. Why don't we? So I'm going to close that. I suggest you save your sims because they will just close. This, of course, is the template. I don't want to edit that. Now we're going to load in a fully completed sim. Actually, the same geometry. Actually, let me do this. There's a current sim. It's in box of the exact same geometry. We can look at everything. Everything you want to look at. Now these files do end up getting pretty big, 1.6 gigs. And of course the hardware, please don't run this on your laptop. Just don't. It's really bad for your laptop. Your laptop will be as horrible as mine. But yeah, here's our sim. Now of course you notice I opened it from File Explorer. What this does is it defaults and opens on a singular core. So let's close that. And then reload it on our 8 cores. Because it will actually take a long time to open up scenes. Now, I'm pretty much going to show you, well, what you do after it runs. Like cooking shows, they put it in the oven and they take the one out that's already done. So first, we have everything here. Everything is great. Let's go to reports. Or let's go to plots first. So this is our residual plot. Anything past 10 to the -3 is considered converged, or when all the residuals are past 10 to the 3. It's a little rough convergence. It's not the smooth curved lines that you lovely want here, but there's some, sharp peaks. But this is pretty good. And of course, if I can move this, our drag has leveled out and our downforce has leveled out. So I would say this is converged, and this is done well. Of course, we can also have reports. We can get our accurate numbers. It'll take a while, as it always does. But yeah, we have an exact value, tons of decimals, you know, what's not to like. But now we want a visualized solution. That's what's really important here. Visualized solution. I actually didn't go over this, and I should go over this now. There's a way to make ISO surfaces, which are a confusing thing, but you pretty much go right click, new ISO surface, and pretty much you select a function. And there are two that I use, Q criterion, which is already there, of course. And what this does is measures your vortexes. And the second here measures turbulent kinetic energy, and it both asks for a reference value. And that is pretty much just take these, but it shows the value. Yeah, take these values, and they will give you a good visualization. We'll see that pretty soon. You'll see it now. So first, let's go to scenes, turbulent kinetic energy, and it's pretty easy to build the scene actually. All you do is you make surfaces, new display or surface, and you just load these in. You can change the color too, although it's a little tricky to change the color. You have to like come in here and change this to content, but let's actually show you what it is. So pretty much this is, you can see all the turbulent, or the vortexes that generate. Pretty much, mainly you're seeing this. Wow, look at that vortex. Pretty big vortex. Some vortex on the outside. And of course, vortex is created by the rotation of the wheel. If you turn on this is your turbulent kinetic energy. Changing the reference value, of course, change what you see. You know, if you lower the reference value of Q criterion, you will see more and larger vortexes. If it's too low, it will just be blue. So you want to keep it, you know, a good value. But this is Q criterion and turbulent kinetic energy, and it really helps you visualize this vortex creation, and hopefully a vortex creation on the outside, or how the tire wake moves generally. Now let's go to the actual visualization of the flow. Now for these, I use, you know, I've opened a vector scene to show you guys, but I use a scalar scene with coefficient of pressure, scalar scene with coefficient of total pressure, and a vector scene. Now these are pretty simple. You go right click new scene. After you're there, you open this, of course. You will set the scalar field as total pressure coefficient. You'll set a min and max. So you get these clipped. It shouldn't be clipped, but you'll set a min and max value, and you will pretty much load all your planes into it. What you can do is pretty awesome. You can go through each single plane and pretty much look at it as, look at air, how it flows around. So ambient is white. As you hit your geometry, you get, you know, separation here, and you can visualize the flow. Look, if we keep going, we now have some sort of system here. We have separation here a little bit, and then as we go on, you know, maybe we're spooling up a vortex here, and if you get later on, you know, you got this vortex creation here, and you can go through these planes and visualize how the air is flowing. You got some loss here, vortex, you know, and you can pretty much go through all these with total pressure coefficient, which this means pretty much ambient will be the highest, and the more you affect the air, the lower it will be. So these, you'll have low pressure in the middle of a vortex, obviously, as air is going very fast there. Well, take it with a grain of salt. But and you get, you're hitting the tire now. Now you're at the tire. How is the air reacting? How is this vortex reacting? Um, Spoiler alert, it gets destroyed by the tire. Well, eventually it does. Yeah, the vortex is gone now. But you have this inward vortex, and you can see that. You can see the difference. And of course, this is consistent with what we saw in turbulent kinetic energy. Now, of course, the other scene is pressure coefficient, a little bit different, but you're just going to see these pressure coefficients, you know? Let's make sure these are clipped. Clipping is bad. All right. But yeah, you have low pressure under the wing, high pressure on top of the wing. You know, pretty simple stuff. You can just go through these planes and see how the pressure field interacts. And then, of course, velocity, vector scene, which I showed earlier. Front. Just having that so easy to do that, just the F key. Yeah, now you're seeing, it's hitting something, it's going away, and you can pretty much go down here and visualize how air reacts. What's a good scene? I think this is pretty good. 9 is pretty good. I know 9 is good, but you see this vortex here, and you can actually see the difference. You have this big vortex here and this sort of velocity area, but at the end of it, you can see the difference between the aggressive, the slow tower, and this powerful vortex here, which is very interesting. You can really visualize that, and pretty much you can use all three scenes in conduction to really visualize the flow. And the final thing is scalar scene geometry. Let's look on that. And this just shows us the pressure. This is the same thing, but instead of parts, you're just dumping in two regions. And you're setting, pressure values. Let's not click these again. But pretty much, if you use the keyboard shortcut, top, you can see the low pressure here. You can see the low pressure, you see the high pressure on the wings themselves. And you can say, well, there was a vortex right around here, and that's why there's, would be less low pressure, sorry. And you can pretty much try to see how the three-dimensional effects affect the actual pressure and the downforce and drag of the wing. You can also look at the tire and be like, oh, there's a low pressure system here. The wing is creating low pressure right here, which is in turn realistically definitely decreasing drag by just creating all this low pressure on the tire. With the outwash, you're getting this outwashing profile. You can just look at this and just look at everything here. And of course, what you can do also is take two designs, put them like this, and see, realize what area is losing or gaining downforce, which is very cool. And so this has been, I guess, my STAR-CCM tutorial. Let me close this. Once again, you can do this all yourself. I urge you to do this all yourself. It's really cool to learn, but after a while, you can use my templates, or you can make templates. You can just go mesh, clear generated meshes. It will clear all the mesh, the solution. You can go clear the solution, clear the mesh, and pretty much if you do all that and you delete the geometry, you pretty much make yourself a template. It becomes a template. And I guess that's all I have for this tutorial. So, thank you.